We are working on Spring Review Worksheet 1, and so now we're on number 5. So number 5 says use implicit differentiation to find the derivative for our expression here, our equation here. Now with implicit differentiation, what that means is when we find the derivative, we're going to have a bunch of y variables that we're going to have to keep track of their own separate derivative, and so each y variable will produce its own dy dx. But first, we want to try to take advantage of any expansion properties that we can do. So I see a natural log of x over root y. We can apply the quotient property, natural log of a over b. Can be expanded into natural log of a minus natural log of b. And when we do that, we can also rewrite the square root of y as y to the 1/2. And then we can bring that 1/2 down in front. And then we have natural log of x minus 1/2 natural log of y, and then the rest of the equation. Now these are all going to be separate terms, so we can apply separate derivative rules for each of these terms. So first, natural log of x, the derivative for natural log of x is u prime over u, so 1 over x. 1/2 natural log of y, 1/2 stays, it's a coefficient. Natural log of y becomes 1 over y dy dx. E to the 2y becomes e to the 2y times 2 dy dx. Remember that the rule for e to the u is e to the u times u prime. So the derivative for 2y becomes 2, and then because we have y derivative, we have to include dy dx. Now, next term, keep in mind that pi is just a number, so 5 times pi doesn't turn into 5, even though pi looks like a variable. But this is just a number, so a number's derivative is just going to be 0. 5x becomes 5, 3y squared becomes 6y dy dx. Now that we found a derivative for each of the terms, we just want to rearrange and move all the dy dx terms together on one side, and then subtract or add all the other non-dy dx terms over to the other side. So the 1 over x can move over, the negative 5 can stay, and once we have the left side all grouped together with all the dy dx's, we can factor the dy dx term out, divide the parentheses over, and then we have our derivative where all of our x's and y variables and constants are on the right side. Okay, number 6, next page. Number 6 says find the equation of the tangent line. So to find the tangent line equation, we need to first find the slope. So to find the slope, we need to find the derivative. To find the derivative, we look at our rule. This is for e to the u. The rule for e to the u is e to the u times u prime. 2 stays, so 2e to the u becomes 2e to the u times u prime. The derivative for 4 minus x is negative 1. So here's our derivative. I can push that negative 1 out in front and make it negative 2. Once we have our derivative, this is our slope formula. If we evaluate the derivative at the x value, so we're concerned about what is the slope at this particular point. So we can plug in 4 in for all the x's. So we get negative 4e to the 4 minus 4. 4 minus 4 is 0. E to the 0 power is 1. 1 times negative 2 is negative 2. So we have our slope there. We have our slope at negative 2. Our ordered pair is at 4, 2. Point slope form. So y minus 2 is equal to negative 2x minus 4. All right, number 7. We want to find the antiderivative involving integrals. But notice that there's only one term in the denominator. So if there's only one term in the denominator, we want to explore expansion power rule first. So we want to bring the x cubed up to the top, but when the x cubed comes up to the top, we have to change that positive to a negative exponent, and it's going to turn this from a division problem into a multiplication problem. So to ensure we do that, when we bring the x cubed up as x to the negative 3, we have to make sure we put parentheses around all the numerator terms as a reminder that we want to distribute that x to the negative 3 through so that we can clean everything up so that we can use power rule. Now when we expand, when we distribute, we're adding exponents, right? So 1/2 minus 3 gives us -5 halves. 2 minus 3 is -1. So now we have nice clean rules that we can apply. The first term is power rule, but the second term is going to be a natural log rule. So the integral for 1 over x is going to be natural log of x. Okay, so we bring down the power rule, natural log of x plus c. So here we have our indefinite integral. Okay, so number 8, cotangent of 4x minus secant of 2x. We have separate rules for cotangent and for secant. The rule for cotangent is natural log absolute value of sine of u plus c, and secant 2x becomes natural log secant u plus tangent u plus c. Now we need to do u substitution for each of these terms. So with 4x being inside the parentheses, that's going to be our u value for the first term. 2x being the u value for the second term. So we apply u substitution separately. U value is 4x here. We find the derivative. We solve for dx. We get du over 4. We clean everything up. We get everything in terms of u and du. And once we have that, 1/4 comes out. An integral of cotangent of u is just natural log absolute value of sine u plus c. Secant 2x, same idea. We clean everything up. We get everything in terms of u and du. We push the 1/2 in front, and then we follow the rule. So integral of secant of u becomes natural log absolute value of secant u plus tangent of u plus c. Okay. There's a negative that sits between the two terms, so we have a minus sign that separates the two terms. All right, number 9, we have a complex looking problem. But first thing is, well, we know that one rule is not going to be able to handle this, so we're going to push this into a u substitution type of problem. But to do that, let's first get that denominator to show parentheses. So we can rewrite this as parentheses to the 4/3. We can push that parentheses up to the top, and then what's inside the parentheses must be our u value. So we say our u value is 1 minus 3x cubed. Find the derivative. 1 goes away. Negative 3x cubed becomes negative 9x squared. We cross multiply. We get dx equals du over negative 9x squared. We substitute the parentheses with our u value. We substitute the dx with du over negative 9x squared. We get the x squared to cancel out. We push the negative 9 out in front along with the 5. And now we apply power rule. So the integral for u to the negative 4/3, we add 1, which is same thing as 3 over 3. So we get negative 1/3 over negative 1/3. We push that negative 1/3 out in front, flip that fraction, and we get negative 5/9 times negative 3 over 1, which is 15 over 9. Replace the u back in terms of the parentheses, and then bring the u, or the negative exponent, back down to the denominator. Okay, number 10 is a washer method problem. This is revolving the shader region around this axis of revolution. So we see that there's a gap between the axis and the shader region, so we know we have to rely on 2 radius. One radius will extend from the axis all the way to the furthest boundary, and the second radius is going to extend from the axis to the closer of the 2 boundaries. So we know that little r is going to be smaller than big R. We also need to find the intersection. So the intersection, we set x cubed minus 1 equal to 26. Solve for x, take the cube root of both sides, we get 3. So we can tell that the left bound must be 0, the right bound must be 3. So then we can plug that into our washer method formula. But first we need to also find big R and little r. So big R is the top of the radius minus the bottom of the radius. So top of the radius is sitting at the 26. The bottom of the radius is sitting at the negative 4. So 26 minus the negative 4, top minus bottom, ends up being 30. Little radius. So we look at the top of the little radius, see what it's touching. It's touching the curve. That's the x cubed minus 1. minus the axis of revolution, which is the bottom of the radius. So x cubed minus 1 minus negative 4, the two negatives becomes positive. We get x cubed plus 3. So now we have big R squared minus little r squared sitting between our bounds of 0 and 3. We make the calculator do the rest of the work, and our volume is 2239.071 pi cubic units because we're dealing with volume.